In this video, I'll be attempting to explain scientific notation. Let's start with why it exists. Consider the mass of the Sun. An inconveniently large number to write. If only there was an easier way. Let's now consider the charge of an electron, which, once again, pretty inconvenient to write. Let's go a little bit further. Let's consider a googol, a number that inspired the naming of the Google we're more familiar with. So obviously I'm leading into this easier way, which is scientific notation, but how does it work? Consider 2.5. If we times it by 10, we get 25. If we times it by 100, we get 250. 2.5 times 1,000 is 2,500. And 2.5 times a million is 2,500,000. This is the train of thought behind scientific notation, but we can write it a little bit simpler. Consider that 10 is just 10 to the power of 1. Consider that 100 is 10 to the power of 2. 1,000 is 10 to the power of 3. And 1 million is 10 to the power of 6. And so while this one here was technically longer to write, this simplifies greatly the writing of our larger numbers. And it can even work for smaller numbers too. Let's think about 1.2. 1.2 times 0.1 gives us 0.12. 1.2 times 0.01 gives us 0.012. 1.2 times 0.001 gives us 0.0012. And 1.2 times 0.000001 gives us 0.000012. Let's try our scientific notation again. 0.1 is 10 to the power of minus 1. 0.01 is 10 to the power of minus 2. 0.001 is 10 to the power of minus 3. And 0.000001 is 10 to the minus 6. Making our very small numbers much easier to write. As a little trick, you might notice that our 10 to the power of minus 1 has 1 0, our 10 to the power of minus 2 has 2 zeros, 10 to the minus 3, 3, 10 to the minus 6, 6. Let's look at our numbers from the start again. Instead of 19900000000000000 kgs, we can simply write 1.99 times 10 to the 20 kilograms. Instead of our 0.0000000000016 coulombs, we can write 1.6 times 10 to the minus 19 coulombs. And instead of our googol, which I'm not going to attempt to say, we can instead write 10 to the power of 100. I hope this helps you appreciate what scientific notation is and just why we need it. These numbers that are significantly large or significantly small are not uncommon in the fields of particularly physics and chemistry. Another way that we can describe scientific notation is to say the power is the amount of times the decimal point is moved, right if it's positive, left if it's negative. So what does that mean? Let's look at 3.6 times 10 to the 12. What this says is that our decimal point moves 12 places towards the right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, all the way over to here. So let's fill in our zeros. And so there's our number. Let's now try a smaller number. Our rule tells us that our decimal point here must move 8 places, but this time towards the left. 1, 2, 3, 4, 5, 6, 7, 8, putting our decimal point right here. So let's once again fill in our zeros. And so there's our number. I'm going to finish on a final point, which relates more to NCEA Level 3 physics. Why in the exams do we see them write 5.00 times 10 to the 2 instead of 500, which seems to make much more sense? Put simply, to make it clear that the zeros are significant figures. For example, let's look at our 500. Now, is this to one significant figure? Is it to two significant figures? or is it to 3 significant figures? Unless we're specifically told, we don't know. There is nothing to indicate whether these zeros are significant or not. With our 5.00 times 10 to the 2, on the other hand, we make it clear that the zeros are significant because otherwise we wouldn't write them. If it was one significant figure, we'd just write 5 times 10 to the 2. If it was two significant figures, we'd write 5.0 times 10 to the 2. And if it was three significant figures, we'd write 5.00 times 10 to the 2. One of the reasons this distinction is important is because the proper convention is to write your answer to the least amount of significant figures given. I hope that's been of some assistance.